So I'm a physicist. I do have a PhD in physics, but I actually became a physicist in middle age. I didn't really know any physics when I studied physics. As I found out, it's a pretty deep discipline. And I work with a bunch of people, mostly from Eastern Europe, so and United States. And we actually, we're working on molecular calculus. So everything that you talk about here, everything I hear, everything you want to do is actually something that we would like to model. So we would want you to actually be able to do this on the computer first. So this isn't like, nothing I'm going to say here in this talk is that deep or complicated. You can corner me later and I can discuss it at any detail you want and as deeply as you want. But most of the things in this talk are pretty easy. So if you look at this house, it was built with some modeling, not too much, right? But if you just go outside this house on our computer or the car or the GPS system, that's all done with physical models, right? We don't even think of them as such. Like Autodesk can tell you how strong your beam is, and that comes from Newton and some other people. Your GPS actually has a relativistic correction in it, which is something I found out recently. It's important. It's not necessary. The engineers didn't think it was necessary, so they have a switch. They put a switch in to turn it off, and it doesn't work as well if you don't have it. So Einstein's theory of relativity is not just, so you're nodding, right? So you know this, right? Okay, good. I didn't know this. So not only is it something you read about in New York Times, oh my God, like some planet. Actually, it's in the phones, it's in the GPS satellites, right? So we have an amazing modeling ability that we also take for granted. Gravitation was invented some years ago, some centuries ago, but we use modeling all the time. We started out with pen and paper, then slide rules. We used some very primitive computers to send a person to the moon, or some people to the moon, or a dog, or into space. Everything you have around you is modeled in one way or another. Like probably 60% of the R&D and chip design is actually modeling and not actually the physical manufacturing. But the machines you're talking about here, all those things are actually, we know the laws that govern them. They're quantum mechanics, and computationally we have them. We absolutely do have them, but I'll show you in the next couple of slides, we have absolutely no way of predicting the nano world, the molecular world, in the same way we expect everything else. We're not even talking the relativistic corrections here. I'll show you what we're talking about here. It's actually quite ridiculous. So I'm sorry, like I'm a bit pretentious. So this is from a movie that some people may know. So if you just put sugar in your coffee, all of you have put sugar in coffee before, right? Maybe this morning. So, and I ask you, without doing an experiment, how well will it dissolve? Just a simple question like that. And this is just, sugar. This actually is not sugar on the picture, but to make it a little simpler. So the answer will be wrong in one way or another using state-of-the-art techniques, right? The answer will be wrong. Well, the answer could be intractable, but if it's tractable in one way or another, it's wrong by something like 5 kilocalories per mole or 6 kilocalories per mole in some direction, whatever, it's plus or minus. And just to give you an idea, the sort of the thermal noise in this room, or any room pretty much, is about half a kilocalorie per mole. And the answer a medicinal chemist expects, like, should I put a phenol or a benzene ring here? You need to be precise to within at least half a kilocalorie per mole or better, just for them to listen to you, right? So we're talking just, so that's just what they expect to see. So just something like sugar and coffee without doing an experiment, without knowing anything about any other experiments, any similar things, you're really quite off. If you talk about a battery and an electrolyte and a lithium ion, then the answer is, again, plus or minus to some degree. You don't know where exactly it lands. They're off by something like half the temperature of the sun, right? So that's not relativistic precision for GPS modeling, right? So that's the next slide. A similar thing happens in some models that a friend of mine designed originally in the 60s are used commercially. They are over 60 years. They have gotten to some decent state, but when you start talking about any molecular system, essentially Each answer is a random number. They do some tricks to make it not so. So recently, actually, I'm not unhappy about this. This is actually a great idea. AI came in, machine learning. Machine learning needs data, and it can make sense of data, right? So people actually realized that for the past 30 years, we have been solving protein structures, and we have a pretty large database of those. And those are only made up of 21 pieces, so 20 amino acids and the backbone. And so you actually have a lot of data on how 21 molecules can fit together. But actually, it's a little misleading because I can show you and I can talk to you about it. Proteins actually prefer to fit together incredibly flimsily and loosely, right? It's not actually, if you just randomly take one of those and let it go, it will not want to go there at all, right? But we do have information on how a protein folds. So this is a problem not solved by physics, but by AlphaFold. Essentially, through a lot of data and AI, evolution was decoded. So a specific, very specific subset of chemistry or biochemistry was decoded. But when you try to take anything not in that 21 set and see how it would fit, not even how well it wants to be there, but just how it would fit, right? The correlation is 0. So, it's a meta study. And of course, that's just how it would fit if it wanted to. Whether or not it wants to, there's no information whatsoever, right? So anyway, so quantum computing, that's a whole story, but the very short story, it's a wonderful thing. Quantum computing is not good at computing quantum mechanics. If it is, it will be actually, it will scale very badly. So it's very good for cryptography. That's why there's a lot of money in it. So why is this so? Especially for biology, this is really so. Biology is, I have many slides to explain this. It's kind of a key point. But this is an example of, let's just say, I apologize, you did say drugs are not a good idea. They are actually exquisitely intricate, physical systems. So if you just wanted to see if this drug piece is okay, or should I put something a little different? And the answer, I tell you, the answer that you expect to get, the precision, the accuracy you need to get is about 0.5. But the actual numbers, and these are not just entropies, this is only energies. The energies involved in these interactions, and between this is aspartic acid. It's a right between this, and the water and various pieces around it are like 20, 30, 40 kilocalories per mole. So basically, you have numbers like 30, plus 30, minus 25, plus 35, minus 15, and so on and so on. And they should add up. In this case, they add up to -2. This is how you live. This is why you are not a rock, right? This is why these machines actually are so intricately, that's why they function. Because you have some very big numbers, and then something changes, and then the big balance shifts completely to you, to the other side, but very delicately. Because it was fast. If it were fast, you would actually punch or move your hand in a microsecond, but that's not what happens, right? So by design, these are very complex. We call them complex systems. Well, they are actually complex on purpose. That's how they are so rich, right? That's how you can build such an important thing. So what this is actually, this is not an easy problem. There's a reason why modeling doesn't exist for these systems. It's a very difficult problem. And if you don't have a sufficient amount of accuracy, it's just like when you go to the optometrist, you can't just say, well, I have less focus, so I have less information. Actually, beyond a certain amount of focus, you have no information. You can't read, the chart. That's it. And that's roughly why it's so difficult to model biology. So I'm saying here, I'm very convincing, I'm sure, but some famous people have said the same thing, and they put down some, so there's two ways to look at this. One is like sort of visionary, and the other one's very prosaic, right? One is a very famous person at UCLA said that this is a holy grail, some of these things, and they'll be accomplished somewhere around, 2070. And another way of looking at it is that people who try to make money from this are not worth anything compared to all the other people. And a bunch of people decided that this had to be done outside of academia, so they got a lot of money to solve it. As I said, right, there's no mystery how we solved it. We just made a Newtonian system that has an equivalent energy to a quantum system. That's it. That's it. It's not like I can tell you how, that's complicated, but and clever and beautiful, but this is basically the idea. And now, the group of people I'm working with can get you the right answers. If you want to put a lithium ion into a battery, if you want to design a drug, if you want to dissolve sugar in coffee, if you want to do anything you want, we can do that. There is actually AI in it, but not gratuitously. It's needed, and I can explain if someone talks to me why. And I think that's it. And we have some results we've published, we've proven it. This is a very nice thing. I just made the slide. I should just get rid of it because I like it too much. And we formed a company recently, and we're raising money to take this into the world. That's it.
Thank you, Boris. Okay, questions, comments?
I want to talk.
Yeah, we can look. I mean, if anyone wants to know how it's done, I think I have another PowerPoint and my whole laptop, so I can talk forever about
How
it.
extensible is the system you're using? I mean, there's an AI component.
We use AI. We use perceptrons. Let's
Okay,
just, I'm allergic to that word a little bit. Sorry. We not for fundraising though. We use that's right. Yeah.
So true.
Yeah. We use neurons. You can think of them as a formula. So that's at some point analytical expressions are not sufficient. These things have certain advantages and also speed of execution, and flexibility, but they have downsides. So we use it. They have very little inference in physics, actually, right? But physics has pretty fantastic inference in physics. So you have to combine the two. Yeah.
Great. Well, you guys should
Yeah.
talk.
Yeah. Okay. Yeah. Yeah.
Okay, thank you.